In this video, we'll be going over op-amp theory, negative feedback, and a simple discrete op-amp design using transistors, such as the one you're seeing here. We'll test our simple discrete op-amp using Digilent Analog Discovery Pro later in the video. In this video, we'll look at operational amplifier theory, covering the basics, looking at the open loop system, and then seeing how we can close the loop using negative feedback. We'll then look at a very simplified discrete op-amp design, discrete meaning made out of individual transistors, and we'll look at the differencing amplifier stage and the voltage amplification stage, or VAS for short. Then we'll look at the PCB I showed you at the beginning of this video and do a little walkthrough in KiCad. Finally, we'll use the Digilent Analog Discovery Pro to do a real-world demo and tests of the real-world system to see how it performs and see how it performs in comparison with simulation. Thank you very much to Altium for sponsoring this video. If you'd like to try out Altium Designer for yourself, they're offering a free trial of Altium Designer if you go to altium.com/YT/Phil's Lab. Once you have your free trial, I'd recommend checking out my STM32 PCB design complete walkthrough for Altium Designer, which is a just under 3-hour video teaching you all the basics from the start of Altium Designer to getting your product manufactured and produced. A big thank you also to JLCPCB for sponsoring this video. The PCB you saw at the beginning and the one I used to implement this discrete op-amp design was manufactured and assembled by JLCPCB in China. If you'd like to have this PCB made for yourself to try it out, maybe make some modifications, you can visit my GitHub account at github.com/PMS67 and navigate to the negative feedback demo repository. Let's briefly go over the op-amp basics. Schematically, you will see op-amps drawn like this: a triangular package with 2 input pins, the non-inverting input V+, and the inverting input V-, and an output V-out. We also need to supply power to our device, and that typically is a bipolar supply, but in our example, I will just be using a single supply with VCC and ground. Essentially, this op-amp is a difference amplifier. Whatever input voltage we apply across these pins is subtracted, multiplied by a very high gain, we'll call that A, and fed to the output. Op-amps typically also have a very high input impedance, seen at the input over here, and a very low output impedance seen at the output. As I said before, op-amps typically require dual supplies, so a positive and negative one with respect to ground, but we'll be using a single rail supply for simplicity. The governing op-amp equation is this one here. Our output is our very large open loop gain A multiplied by the difference at the inputs. This is usually enough to solve most op-amp circuits. But to get any useful circuitry with op-amps, we actually need to use negative feedback. So we take some part of the output V out, divide it down via some fraction, and feed that into our inverting input because we want negative feedback. And we'll see why in just a second. An alternative view of the op-amp is this open loop block diagram, and hopefully this will simplify things a bit more. We have a difference at the beginning, simply subtracting V- from V+. The output of that is then amplified or multiplied by our gain. So we take our difference and multiply it by this constant A. Implicitly, our op-amp and in the real world will have some sort of bandwidth, so some sort of upper limit of frequencies it can handle before the gain drops. The cutoff frequency is typically denoted in radians per second, and our conversion is simply 2 pi times the frequency in hertz. Now, as I said before, we would like to feed some part of the output back to this inverting input. And this is what we then typically call a closed loop system. We have closed this feedback loop. The way we do that is feeding back a fraction of the output, scaling it via this constant B, and then feeding it to the inverting input. B typically is a fraction between 0 and 1. The question is now, why would we even want to do that, and what effects does this have? To do so, we require a tiny bit of maths, but don't worry, this isn't too complicated. We'll assume that we just have a single input for now, essentially that our non-inverting input V+ is equal to V in, just for simplicity, and we have a single output, which is V out, which is our normal operational amplifier output. We want to now find the relationship between the input and the output. So if we apply a signal to the V+ pin, what is the signal to the V out pin? Let's start off by ignoring the bandwidth. So let's get rid of this block for now, and then we just see the output is A times the difference at the input. V- we said is a fraction of the output, which is B times V out. So we can substitute this expression into this. This is what I'm doing here. And then I can rearrange for V out divided by V in, and we typically denote that by the gain. For example, if we have a gain of 10, if we put a 1 volt at the input, we'll get 10 volts at the output. It turns out our gain expression is this over here, A over 1 plus A times B. Remember, A was our very large open loop gain, and B was our feedback fraction between 0 and 1. This is all very good, but why is this useful? It turns out that the open loop op-amp gain A is actually very uncertain, but it is very large, usually on the order of 10 to the 5, 10 to the 6. But this could be 2 times 10 to the 5, it could be 10 times 10 to the 5, so rather uncertain. B, on the other hand, is something we can control. We choose our feedback fraction, we say, okay, this is 0.2 we're feeding back, or 0.371, so we can control it very precisely. It turns out that if A is very large, and looking at this fraction then tends to, as A gets very large, to 1 over B. So this is really cool because essentially our gain of this closed loop system does not depend on this very uncertain gain parameter A, which is intrinsic to the operational amplifier. So simply by varying our feedback fraction B, we can get a very precise gain of this closed loop system, so a very precise amplification. And this is pretty much independent of A, as long as A is very large. The nice thing is, this is not the only benefit of using negative feedback. It can be shown that negative feedback, in the way we've applied it here, where taking an output and providing some sort of fraction back to the inverting input, it increases the input impedance, so Rin of the amplifier is increased. It decreases the output impedance, which means Rout is decreased. It increases the linearity, so reduces distortion. And it increases the bandwidth of our amplifier, so this section over here. Just to show you why the bandwidth is increased, we can actually take the bandwidth into account into our equation. Simply, our output is now a function of frequency, and I'll just use angular frequency for simplicity, and that is omega. So we have A times V plus minus V minus times this new frequency-dependent term, which is a simple first-order low-pass filter with a cutoff frequency of omega c. Applying the math we did before, but in this case including this term, we find that we have our typical expression A over 1 plus AB, but we also have this frequency-dependent expression, which is now scaled by 1 plus AB. Now if you compare this form here to this form over here, we see that our cutoff frequency is increased by a factor of 1 plus AB. So the closed-loop bandwidth, by applying negative feedback, is increased by this factor of 1 plus AB. This is illustrated on the right here. This is our open-loop bandwidth. We have very high gain with a certain cutoff frequency, and once we apply negative feedback, we are sacrificing gain. So you can see our straight line moves down, but we have increased the cutoff frequency by moving along this slope to omega c 1 plus AB. So this is pretty cool. But this illustrates the sacrifice between gain and bandwidth. Nothing's always positive, and of course we have negatives even with negative feedback. Anytime we use feedback, we need to worry about stability. Essentially, we don't want our negative feedback to turn into positive feedback. Positive feedback is very helpful in certain situations, for example, if you want switches and things to change very quickly. However, in our case, we want controlled negative feedback that is stable. Positive feedback leads to saturation, for example, an input saturating the op-amp and making it hit the supply rails, or oscillations. And these are very harmful to the op-amp itself, as well as to surrounding electronics or connected electronics. Now let's see how we actually implement this feedback fraction B in a real circuit. And the circuit on the right here is something you've probably seen many times before. It's the classic non-inverting operational amplifier using 2 external resistors. Essentially, our feedback fraction is determined by these 2 resistors, R1 and R2, and they form what is known as a potential divider. And we can make these resistors rather precise, for example 1% tolerance resistors, and this again is to show that we can make B very precise and A is rather uncertain. The feedback fraction is simply calculated by this divider ratio, and that's R2 divided by the sum of the resistances, so R1 and R2. Now plugging this into our equation, remember we saw our closed loop gain is 1 over B, as A is very large, and B is our feedback fraction, so our overall closed loop gain turns out to be 1 plus R1 divided by R2. And this is the equation we are very familiar with a non-inverting amplifier. Now we've covered basic op-amp theory, we can move on to a very simple discrete op-amp design. We'll go through section by section, but in essence and in most op-amps there are 3 main sections. There's the difference amplifier, which we saw before, which essentially takes V plus and subtracts V minus. This difference amplifier can also have some gain of its own. The next stage is typically a gain stage to provide further amplification and increase the open loop gain A. And I'll call that the voltage amplification stage, or VAS for short. Most op-amps will also have some sort of output stage. This is so that the op-amp is able to drive fairly heavy loads. However, I have not included this in our design, just for simplicity. You can also see here I've left in this bandwidth section. But the bandwidth is pretty much implicitly limited by the circuitry, so by the transistors, the capacitances, and so forth, and the design itself. So what we have to design is essentially the difference amplifier and the gain stage, and of course then an output stage if you require this. Keep in mind that discrete operational amplifiers are usually and mostly vastly inferior to dedicated IC op-amps. And this is simply to demonstrate some of the internal workings of traditional op-amps. With any design, we need some sort of goals or requirements. For our design, I said before, we want some sort of single supply operation, and for operational amplifiers, we also typically want a high common mode rejection ratio, or CMRR for short. Essentially, common mode rejection ratio means we amplify differences, so if V plus is different to V minus, and if V plus is equal to V minus, we don't want any of that to leak through. So we only want to amplify differential mode inputs, not common mode inputs. We also want a very high open loop gain, and we saw why before. And of course, we need to take care that this amplifier is stable for various gain settings, and we have a fairly reasonable bandwidth, especially when we go over to closed loop. Optional, we might want to be able to drive various loads, capacitive, light loads, heavy loads, and so on. But let's start off with the difference amplifier. Again, the difference amplifier takes V+, subtracts from it V-, maybe provides some gain, and then forwards that to the next stage. The way we typically implement that, and most op-amp ICs will of course have that, is in the form of a long-tailed pair, which you'll see over here. In its simplest form, the long-tailed pair, or LTP, is simply a pair of bipolar transistors or field effect transistors. This BJT pair, if wired up in a sensible way, amplifies the voltage difference. Again, primarily, we will have some common mode amplification, but we primarily want to amplify the difference of the signals seen at these bases. So as before, our output voltage, which we take at the collectors, is some sort of gain of this stage times the difference. This is our ideal case. Another thing is we have our differential input signal to provide a single-ended output. So it performs some sort of differential to single-ended conversion and enables us to provide some sort of input at the non-inverting terminal, as well as to use negative feedback with this inverting terminal. Now you can see here we require some sort of load, and in our case we'll be using a current source. In essence, for any transistor amplifier, the transconductance of the amplifier times by the resistance of the load is the gain. Current sources have very high impedance, so we get a very large impedance of the load, and that improves our gain. So our gain is improved by using a current source. Below here, we're using a current sink, and this improves the common mode rejection ratio. Now going over briefly to KiCad, here I have the schematic of the final design, and this is a bit more complicated than what you saw just now, but in essence, it's the same thing. We have some sort of current source at the top here, we have our differential bipolar pair, and we have a current sink. The circuitry around it is for biasing, it's for filtering. For example, we have our power input over here, we have some small decoupling, we have emitter degeneration resistors over here, here, and these two over here. This is to help with matching and also provides its own form of local negative feedback. The current through this long-tailed pair is essentially going through this transistor, but also through this one here, which is part of the current source, and R6 over here, the 22 kilo ohms, sets the current. Essentially, we have our supply voltage up here, a small drop across this degeneration resistor, then 0.7 volts drop here. So essentially, we have VCC minus 0.7 across this resistor, and this is mirrored in this transistor. So R6 varies our current through this long-tailed pair. I also have some small amount of RF filtering at the non-inverting input, as well as biasing, which we'll look at later. But this is essentially just a current source, the pair of bipolar transistors, as well as a current sink. So exactly what we saw in the block diagram. I've taken that design you just saw and put it into a SPICE simulator. I've chosen VCC to be 5 volts, and that gives me a long-tailed pair current of about 200 microamps. For the simulation, I've simply biased both of these bases to half the supply voltage, and that then is 2.5 volts. By applying a common mode signal, so V plus and V minus the same, I got a common mode gain of minus 42 dB. Alternatively, if I apply a differential mode signal, so V plus and minus V plus to this base here, I get a differential mode gain of 59 decibels, so fairly okay. So the difference in decibels of the differential mode gain and the common mode gain gives you my common mode rejection ratio, which is fairly okay for this very simple design of just over 100 decibels. And here you can see an extract of the Bode plot for this simple design. We have in the passband a gain of 59 dB, and we have a cutoff frequency fairly early at 43 kHz, so a minus 3 dB point over here. Now that we've looked at the difference amplifier, we need to go to the next stage, which then gets fed into, and that's the gain stage, some sort of amplification. And the way we do that is via a common emitter amplifier, so a very, very basic BJT amplifier. We have an input voltage at the base and an output voltage at the collector. We have some sort of load, and we have some sort of degeneration for biasing and stability. This common emitter amplifier is our gain stage, so provides additional gain, but because of its large output impedance, which is largely determined by the output impedance of the load, means it can't drive further loads very well. So this would then typically feed into some sort of output section. Again, transconductance of that transistor times the load resistance gives us approximately the gain. So that's why I have a current source here, because a current source has a high impedance and therefore provides a large gain in combination. You can also see this capacitor between the base and the collector of this transistor. And this is what we call dominant pole compensation. We do a roll-off of the gain above a certain frequency using this dominant pole capacitor. And this is to aid stability for the closed loop. And without this, essentially you get ringing, oscillations, and an unstable amplifier. Because we have gain in this stage, we are exploiting the Miller effect. So any capacitance was seen between the base and the collector of this amplifier is effectively multiplied by the gain of this stage. So actually C-DOM is typically a very small capacitor, anywhere, 22 picofarads to 100 picofarads. We also have this emitter degeneration resistor over here, which provides, again, local negative feedback and is useful for biasing. Now, this emitter degeneration resistor brings benefits, but it also brings that this stage will lose gain. Therefore, I have this bypass capacitor. So at AC, the DC operating point isn't affected, but at AC, essentially I'm bypassing this emitter degeneration resistor, and this improves the overall gain. Going back to KiCad, this is what you can see here. I'm using my current mirror or my current source and tapping off again, and this is my current source for my voltage amplification stage. You can see I've added a couple switches around for my test PCB so I can test different types or values of compensation, emitter degeneration, and bypass capacitors and so forth. So I can switch between 22 picofarads and 100 picofarads with a dominant pole compensation. I have my main amplifying transistor over here, my emitter degeneration over here, and I can switch between two different bypass capacitors, 22 microfarads and 100 nanofarads. And this will essentially shift my lower cutoff point because essentially this forms a high-pass filter. Again, I've run a very basic simulation using SPICE, and the gain of the common emitter amplifier we just saw is about 37 dB. And this is predominantly due to the current source being used as a load. Now, combining this common emitter amplifier with the long-tailed pair we just saw, we can combine the gains in simulation and also look at combined bandwidth. The total gain then is about 96 dB. And we can convert that to RA, so remember our open loop gain, and that's just over 63,000 linear. So pretty respectable for only these two very simple stages. Our bandwidth is pretty shoddy though, at only 2.5 kHz, and this is without dominant pole compensation. If I put in, for example, a 202 picofarad dominant pole capacitor, it drops to 360 Hz. So we get a lot of gain, but not a large bandwidth. However, this doesn't really matter because we're never going to use all of this gain we have anyway. We're going to feed back some of the output back to the inverting input, and then we get a much higher bandwidth. A typical expression you'll see with operational amplifiers is the gain bandwidth product, or GBP for short. Essentially, multiplying our total gain by our open loop bandwidth gives us a gain bandwidth product of 2.3 times 10 to the 7. Now, anytime we want to work out what bandwidth we'll get for a certain closed loop gain, we simply use our gain bandwidth product equals gain times bandwidth. So given this rather large gain bandwidth product, if I want a gain of 10 times, so 20 dB, I simply divide this number by 10 to get my bandwidth, which will be 2.3 megahertz, which is fairly respectable for a simple design as this. Now that we've gone over a very basic design, let's have a look at the PCB and then do some analysis and tests in real time. On the final PCB, I've then implemented our operational amplifier, which you just saw, but also provided some external circuitry, which we'll go through one by one. Essentially, our operational amplifier, as we saw before, in an open loop configuration is a tiny bit useless. So what I've done is first of all provided some sort of biasing structure, here shown simplified just with two resistors, to bias our op-amp at half the supply voltage, to make sure, everything inside the op-amp and the output can swing to its full potential, so to speak. I've AC coupled the input and output because I have to provide this DC bias over here. So I have an input voltage, then a coupling capacitor, the output of my op-amp, a coupling capacitor, and then my output of the system. I've also provided this feedback network over here, and earlier we saw just R1 and R2 to provide our feedback, essentially dividing down V out and feeding it back to the inverting terminal of our operational amplifier. And this essentially sets our closed loop gain. I've added two capacitors, however. The one down here is called CHPF. HPF stands for high pass filter. Essentially, this is then just an AC non-inverting amplifier. The second capacitor, again as the name implies, CLPF, is a low pass filter. Essentially at AC or high frequencies, this low-pass filter capacitor will bypass R1 and thus make this into a unity gain amplifier. So now let's go over to KiCad and have a look how that's then implemented on the PCB. Here I have KiCad open. On the left-hand side I have the schematic, on the right-hand side I have the PCB. So you can see this is kind of a test PCB, nothing to be used, in any proper circuitry, just for us to have a play around with what do various settings in our discrete op-amp design do. First of all, I have two potentiometers, one labeled bias and one labeled FB. The bias potentiometer we can find in the schematic over here, and this essentially is our potential divider, which is variable, which applies a bias voltage to the input of our op-amp, just as we saw right now. And I've made this variable because I want to show essentially if I bias my op-amp wrongly, for example not at half the supply voltage, that I might get clipping at the output, which is undesirable. The second potentiometer is FB, and that is for feedback. And FB we can find over here, and it's this feedback network over here. So this, what we saw before, would have equivalently been R1 and R2. Essentially I can vary my potentiometer to vary my gain. So all the way from 11 down to unity gain using this feedback potentiometer. We also have a couple of switches. Let's start with the compensation switch or comp switch over here. In the schematic, this switches between a 22 picofarad and a 100 picofarad dominant pole capacitor, so we can see the effects on frequency response, stability, and so on. Additionally, I have a bypass switch over here, which, as the name suggests, changes the bypass capacitor value across this emitter degeneration resistor, which was used in the common emitter amplifier stage. Essentially, this will also perform some sort of high-pass filter, so with 22 microfarads, I'll get a much lower cutoff frequency than with 100 nanofarads, and we'll see that in action soon. HPF and LPF, as the name suggests, are high-pass and low-pass filters. As I just shown, I made the feedback network a bit more complicated than just two resistors. I have one capacitor which I can switch between 100 picofarads and 100 nanofarads. With this switch, LPF, where I can change my external low-pass filter in the feedback network, as well as this HPF switch, which switches between 100 nanofarads and 22 microfarads, which changes essentially my AC high-pass filter external cutoff frequency. Then I just have my input up at the top right here, which is the input to my non-inverting terminal via a coupling capacitor. I have my power supply input, again a single supply, and I have my operational amplifier output after the feedback network, and after this, coupling capacitor of course. So let's go over and use the Analog Discovery Pro by Digilent and the WaveForms software to play around with this thing. Here I've got the WaveForms software from Digilent open, and I'll be using this to do a few little tests and experiments, so to speak. The first tool I'm going to use is the WaveGen tool over here, which I already have open. Channel 1 of this WaveGen is generating essentially my input signal, which then hooks up via a coupling capacitor to the non-inverting input of our operational amplifier. Because this whole circuit uses very little current, basically less than a milliamp total I believe, I can use the second WaveGen out to just provide my DC voltage, and I'll just be running that at 5 volts. So this is used to power my circuitry. Now this of course isn't normally recommended, but since I'm drawing so little current and I just have this in place for now, this makes my life a tiny bit easier. To then view my waveforms, I'll be using the scope. So let's start off by looking at the scope section. Channel 1 is yellow, which is the input to my operational amplifier circuit, and channel 2 is at the output, and of course there's coupling capacitors in between. I have my 1 kHz sine wave apparent at the input. I've got 200 millivolts per division for channel 1 and channel 2. It's rather hard to see, but channel 2 is actually right behind channel 1. This is because I've turned my potentiometer all the way down to make sure I have unity gain. So all of my output voltage is applied directly to the inverting terminal of my op-amp. If I change my potentiometer, so I decrease the amount of feedback, decreasing my feedback factor B, I'm increasing my gain, and you can see I get some sort of amplification due to the way I've arranged my circuitry. So it looks like by varying at least our feedback value, so we can change B, we can change the gain of the system as expected. So this looks like it's working. The other potentiometer controls my bias, and I haven't said anything yet, but my bias is currently centered, so this should be at VCC over 2, so about 2.5 volts for supply voltage of 5 volts. Now if I start playing with my bias and moving it away from the center, you will see some clipping occurring. So now I've moved my bias to a place which is very close to one of the supply rails, and you can see I get this fairly asymmetric clipping. And this of course isn't great because we get loads of harmonics in there, and our pure, well almost pure 1 kHz sine wave at the output is rather distorted. This illustrates the fact that we do need quite a good bias supply, at least centered around the middle. So let's move it back to the center, and you can see we have a nice clean sine wave again. One more thing we can look at is this gain bandwidth product, which essentially stays constant for the amplifier. So depending on what closed loop gain we have, we'll also alter the bandwidth. So let's see that in action. The way I'm doing that is by using this network analyzer from WaveForms. And this allows me to scan through certain frequencies. It'll send a test signal at the input and then record the output and measure, for example, the magnitude or the gain and the phase versus frequency. So I've got my potentiometer set to essentially unity gain and my bias at the middle. So let me just run a little test. And as you can see, it's stepping through and we have about unity gain. I've just started at about 100 Hertz just to test. And that's running through to about a megahertz. And as you can see, we've got quite a large bandwidth. Just note that this gain is linear and not in dB. So a gain of 1 over here. So we need to drop down to about 1 over root 2, which is about 0.7. So the bandwidth is, far over 1 megahertz at a gain of 1. But now if I, for example, center my potentiometer, my gain or my feedback potentiometer, and do another measurement, you can see I have some sort of high-pass filter over here, and then I will go into my passband, and then quite soon roll off again. So my gain at a centered potentiometer is about 5.5. So for the bandwidth, we divide by root 2, and that is just under 4, I believe. So somewhere here is our new bandwidth, which is about 350 kilohertz. By increasing the gain of the closed-loop system, I am sacrificing bandwidth. I can do that even to the extreme by turning the potentiometer all the way to the other side, and I get quite a lot more gain at around 10 linear, but then of course I have a much lower cutoff frequency again, I know, something around 100 kilohertz. This kind of demonstrates the gain bandwidth product. So let's stay with this network analyzer and move our gain potentiometer right back to the center and just do one more scan. And now let's have a look at what some of these switches do. For example, I'd like to look first of all at these two external switches here for the feedback network. One, as we said, is for the low-pass filter, and one is for the high-pass filter. Currently, for the low-pass filter, I have 100 picofarads engaged. Let's see how the frequency response changes when I switch that to 100 nanofarads. So I'll switch to 100 nanofarads, like so, and then click another single. And as you can see, 100 nanofarads is actually quite extreme with a combination of about 5 kiloohms, and we get a strong roll-off and a strong reduction in gain. But you can see this is how we can band limit our signal if we don't have, for example, access to the internals of the op-amp and want to apply it externally. Let me flick that back to 100 picofarads and rerun the test. And here we are back to normal. And now let's try this high-pass filter switch. So currently it's at 100 nanofarads, which in combination with this 1 kilo ohm resistor gives quite a high cutoff frequency for this high-pass filter. So that's why we have quite a strong attenuation in the low band here, even below 2 kilohertz. So if I just move that to 22 microfarads, and then rerun the test, you'll see my cutoff frequency is drastically lowered, which means I get much more gain even in these lower bands. But the same, of course, performance in the top band because that is influenced predominantly by this low-pass filter. So now we've seen the effect of these two switches and what these low-pass filters and high-pass filters do. Next, let's look at the effect of the dominant pole compensation. And in a closed loop, this is actually fairly hard to see, but we can see that this influences also the slew rate. So I've gone back to my WaveForms software and I'm outputting a 1 kHz square wave with 50% duty cycle, just so we can see what happens on these rising and falling edges. So my scope, this is channel 2, as you can see, it's trying to slew up to the peak voltage, but it's having a bit of trouble with this rising edge. Now this capacitor is currently on 22 picofarads, this dominant pole capacitor. If I increase it to 100 picofarads, you can see we have even slower slewing. Now, increasing the dominant pole capacitance does improve your stability margins, but of course you'll have much slower slew rate. So I can switch it back to 22 picofarads, and you can see this changes the slope of this rising edge, or how quickly this amplifier can slew. We also see, because we get stable input-output, that for the gains we're looking at, the closed-loop system seems to be stable. Thank you very much for watching this video. If you liked the video, please leave me a like, and if you're new here and haven't subscribed, please do subscribe for more content like this, PCB design, electronics, digital signal processing, and more. Thank you so much, and I'll see you in the next video.